All right, Ozarka here. This is going to be a video on piecewise defined functions, or sometimes they're just known as piecewise functions. First thing we're going to do is define and evaluate what piecewise function even is, and then after that we're going to sketch piecewise defined functions by hand. It doesn't have to necessarily be exact, but it's going to be enough to be able to answer other questions based on these piecewise functions, namely if the function is continuous or not. All right, this next section right here, it says piecewise functions. It says a piecewise function is a function defined, so right here, a function defined by two or more formulas, where any particular formula is valid only for a unique portion of the function's overall domain. So there's an example right here. I'm going to zoom in here just so we can kind of focus on it. One thing that I want you to notice on this is this function, the function's name is f of x, pretty standard for a function name, but it's broken up into two pieces. We have this top piece and we have this bottom piece. And each piece is only defined based on the domain over here. And if you notice, there cannot be any overlap between these. So one of them says x is less than 0. The other one says x is greater than or equal to 0. There's no overlap because if there was an overlap, then it would not actually be a function. So it would still be piecewise, but not a piecewise function. You're not really going to see that overlap ever, but just so you know, that's the main thing to look out here is there shouldn't be any overlap with the x's. And then if x is less than 0, let's just say we used x is equal to, I don't know, -1 or something like that, we would have to use that first piece because it's based on the x value. The bottom piece would be used if, like, I don't know, say the x was 0 or 3 or 100 or something like that. Then we would use this second piece based again on that domain restriction. That's basically how piecewise functions work based on this notation here. We're going to be doing some example problems to kind of show how to use these pieces a little bit more so it kind of solidifies your understanding. All right, this next little blurb here says, when evaluating or graphing piecewise functions, be sure to only use the formula that applies to the portion of the domain that is under consideration. So if you use the wrong piece, you're going to get the wrong value probably. So you're going to want to use the right piece when the x calls for it. For example, the one we just looked at where it says x is less than 0, if x was less than 0, let's just say x was, I don't know, -10, then you would have to use that first piece because if you use the second piece, you can get the wrong answer. All right, examples. It says refer to function f given above. I also kind of copied and pasted it right underneath there. And we're going to be using that piecewise function, that f of x, to evaluate f of 0, f of -5, and f of 3. And it's going to be important to make sure that we pick the correct piece when doing this. So this first one, f of 0. Okay, here the x is equal to 0. That's what this 0 means right here. It means x is equal to 0. So now you have to think, do we use this first piece or do we use the second piece? Obviously, we're going to be using that second piece because it says x is greater than or equal to 0. So we're going to plug 0 into this x right here. So it's going to be 0 squared plus 1, which is very basic math. It shouldn't be too big of a deal. And the answer is 1 for that. The next one, f of -5. So we're going to do this one now. F of -5 is going to be equal to, we have to figure out which piece to use. We're going to want to use the first piece on this because -5 is less than 0. Okay, x is -5 in this case. It's less than 0, so you have to use that first piece. So it's going to be 3 times -5 minus 2. Which means you're going to have -15 minus 2, which is going to be equal to -17. So that's the answer for that one. The last one, f of 3. Here the x is equal to 3, which means it's greater than 0. So we're going to have to use that second piece again. So it's going to be 3 squared plus 1, which is equal to 9 plus 1, which is equal to 10. And you have your 3 answers that we're supposed to evaluate based on that piecewise function. All right, the next one we're looking at, it says consider the following function, g of x. Now it's a piecewise function that has 3 different pieces. And we're going to be sketching this and determining the domain and range for it. So what I recommend doing whenever you sketch these is to make the boundary based on the breakpoints. These breakpoints are all right here. So -1, -1 and 1 and 1 here. So essentially what I'm going to do is just make little highlights of that breakpoint. So for that first one, x is less than -1, I'm going to make kind of a little boundary. I'm just going to highlight it so it's not actually just colored in. It's just kind of for visual reference at x is equal to -1. And then we're going to do another one at x equals 1 because that's also part of that breakpoint. So any values like this -1 here and this -1 here as well, this 1 and this 1, basically what you're going to want to do is make those boundaries. I just did highlighting for it just to make the graph a little bit easier to create. It'll make sense to you once we actually go over this in more detail. First thing we're going to do, it says x is less than -1. So that's this part of the graph. It can't be over here. Okay, it can't be in between here. It can only be this side over here. I'm going to delete all that just to clean it up a little bit. So we can only make that function y equals 1 in this case. It's just going to be y equals 1. We can only make it on the left side of that boundary. That's why it's good that we made the boundary. And it says y is going to be equal to 1. Now, because it's x is less than -1, we're going to make an open circle here on it. And the graph of 1 is just a horizontal line. But remember, we can't go past that boundary. So I'm just going to make a horizontal line here, and it's going to be pointing to the left. It cannot go to the right, again, because it only applies for x is less than -1. The next piece is going to involve -1 to 1. And the formula that's going to define it on that interval is -x. So we're going to plug in, I'm just going to plug in each endpoint here. So I'm going to plug in -1 into this right here. So -1 is just going to be 1, and it's x is less than, or I'm sorry, x is greater than -1. But so we're not going to actually fill in the hole there. So it's just going to still be a hole there because we're not including the value. And then I'm going to do the same thing with this 1. So I'm just basically doing it on both sides of the break-even point. We know it's linear, so we can just do those 2 points and connect the dots. So if you plug 1 into this -x formula here, you're going to get -1. And because it's not included, we're just going to put an open circle here, and it's linear, so we're just going to connect the dots like that. All right, from here, we're going to do the third piece, this side of it over here, which is x is greater than 1. It's going to be equal to -1. Okay, not inclusive again because it says just greater than 1, so make sure you keep it as a whole. And we're going to make a line going across this way, because that's how you would graph -1. And there we go. We sketched the graph of G. Now we need to determine the domain and range of G now. Domain is all the possible x values. And based on this graph, you can see that it goes forever to the left and forever to the right, except here and here, because it's an open circle there. It's not included at that point at any of the holes. So what we're going to do is we're going to go from -infinity all the way up to -1, union -1 up to 1. Again, not inclusive, so we're going to use parentheses, not brackets. And then we're going to do another union here from 1 to infinity. And that is our domain. All right, our range is based on the y values that are in this graph. And the lowest y value that you can have on this is going to be -1. You can just kind of see that looking at the graph. The lowest that it goes right here is -1, and it does not go in a downward direction after that middle point anyway. It just kind of, this part right here stops. But if it kept going, it would be -infinity, but it doesn't do that. It literally just stays at -1, and it's inclusive of -1, so we're going to put a bracket there. Comma, okay, the highest it goes is 1 on the other side. You can kind of see right over here, the highest it goes is 1. It's not going in the upward direction. So it stops at 1. It's inclusive as well. So we're going to use brackets for both of those, and we have our answer. All right, this next part is on continuity, and it says a function is said to be continuous. I'm sure you've heard that term before. Continuous if the graph can be drawn without picking up your pencil. Okay, your pen or pencil, whatever you're using to draw the graph. If you don't have to, if you can draw it without picking it up, then it's said to be continuous. When you take Calculus 1, you'll actually go over another definition of continuity involving this thing called limits, this concept of limits. But for now, just kind of imagine it as you can draw a graph without picking up your pen or pencil when you're drawing the graph. Piecewise defined functions can be discontinuous at break points, even if individual formulas or pieces define continuous functions. So we have to be aware of breakpoints and overall continuity of each individual piece when we're trying to figure out the continuity of a piecewise function. The first example, it says right here, consider the following function. We have another 3-piece piecewise function there, h of x, and it says graph, to sketch the graph of h. Is h continuous? So we're gonna have to graph it just like we just did a second ago, and we're gonna figure out, is it actually continuous or not? If we go back to our previous example, you'll notice that this is not continuous, okay? There's a hole here and a hole here. If for something's continuous, there can't be any holes, jumps, or gaps. In this case, there are, so it is not considered continuous. We're gonna be doing a similar thing. We're gonna be graphing this and basically figuring out if this function, h, is continuous or not. All right, first thing I'm gonna do, just like last time, is I'm gonna make those breakpoints. I'm gonna put a little highlighted there just so it kind of breaks up the 3 pieces. So here's gonna be -4, because it says x is less than -4. The next one says -4 to 4, so we already have the -4, now I'm gonna do the 4. Right, here's 4, and then x is greater than 4. So now we have the 3 parts. If you notice, we can kind of, there's one part here, and one part here. Okay, and it's all based on each of the individual pieces. Piece 1, piece 2, and piece 3. If you really wanted to name them that, you could say this is piece 1, piece 2, and piece 3. It's not really formally named that, so I'm gonna get rid of that, but just if you want to think of it that way, it's kind of a great way of doing it. Okay, if x is less than -4, y is equal to 6. So 1, 2, 3, 4, 5, 6. We're not including it here, because it says x is less than 4. If it said x is less than or equal to 4, we can actually color that in, and then we're just going to graph y equals 6 with arrowhead at the end. Okay, the next thing we're going to do is plot the second piece, -10 plus x squared, and we're going to do it at its breakpoint. So -4 first. I'm going to plug in -4 for this x right here, and it's going to be 16 plus -10. 16 plus -10 is just going to be 6. So this one actually is colored in here, based on the fact that it's got this equal sign right here. I'm gonna do the same thing with the other side. I'm gonna plug a 4 into this as well. Again, you get 16 plus -10. So again, you just get a 6. So at the 4 over here, you also get a 6. And this is quadratic, so you can't just connect the dots here because it's actually gonna be a parabola. So what we're gonna do is we're gonna use the fact that if we plug 0 in for x, you get -10 because it's -10 plus 0. And we end up having something like this right here. And what you can do is just make a parabola. I'm going to do this very roughly. This is just a sketch, so it doesn't need to be exact, but it's going to be something like this. Not exactly the best sketch, but it'll do. The next thing, it says x is greater than or equal to 4. If you plug a 4 into this right here, you're going to get 8 minus 2 is 6. And this was not actually supposed to be colored in initially. So I'm going to make that a hole right there, but this next part will actually show that it is supposed to be because it's x is greater than or equal to 4. This one wasn't, so I couldn't have just assumed a hole based on that second piece. This one is x is greater than or equal to, so now it actually does end up getting colored in, so you end up going the same spot, but I just wanted to kind of show you that for clarity. Now it's 2x minus 2, so from here we should be able to go up 2 over 1, and you end up having something that looks like this. I'm going to connect the dots, and you end up with something like that. Okay, now you need to see, is there any holes, jumps, or gaps? Is H continuous? It is, so the answer for this question would be yes, it is continuous. All right, this next one here is another graphing one. I'm going to, again, highlight those boundaries just so it's a little bit easier to graph this. So we have a -2 boundary, and we also have a 3 boundary. Okay, now this one's only 2 pieces, so one thing I do want you to notice is there's not going to be anything over here. Okay, there is no x is less than -2, so there's not going to be any graph to the left there. First thing we're going to do is I'm going to plug in -2, because that's the breakpoint, into this right here, and it's -2 minus 3 is -5. So 1, 2, 3, 4, 5, and it is going to be colored in because the -2 is included on that. It's less than or equal to. Then I'm going to plug in 3, and I'm going to get 0. And because that's not included, I'm going to make it an open circle like that. And because this is linear, we can just connect the dots. The next piece is x is greater than or equal to 3. So I'm going to plug in a 3 on this. This is linear as well, so it should be pretty easy to do. And you're going to get 9 minus 6. 9 minus 6 is 3, so we're going to be 1, 2, 3 up here. It's going to be included because it's x is greater than or equal to 3. And we're going to go down 2 over 1, down 2 over 1, and it's linear, so I'm just going to connect the dots, and you have something like that. Now, it doesn't ask this, but if it did and it said, like, is this function continuous? Are there any holes, jumps, or gaps? And you can see there is a jump and a hole at x equals 3. So therefore, this would be not continuous. It doesn't ask that, but I just thought I'd point it out. So that's basically piecewise defined functions. We defined what they were, we evaluated them, we sketched them, we figured out if they were continuous or not. If you have any questions about anything in this video, let me know.